Our kind of our learning target for today is, again, we're gonna, like we do with functions, just work on identifying things. All right. If we're given something in, whether it's a graph, a table, or equation, can we determine whether it's linear, and do we have a way to justify that? So a few kind of definitions / vocab, important things to know to go over first with linear functions. A linear function in two variables, meaning there's an x and there's a y, is an equation that can be written in the form y equals mx plus b. Last year, as 8th graders, you all took a class called linear algebra. This should be familiar, y equals mx plus b. Linear means line. You can see the word in the word linear. The prefix is the word line. All right, so we're talking about today about functions that make lines.
Just as a fun side note, geometry next year, just spent 2 days reviewing this stuff.
So yes, if you can have this down and remember it, you're good to go. All right, so that's the form. That's one important thing we'll have to remember. Y equals mx plus b. A linear function, so we're talking, yesterday we talked about functions, now we're talking about a specific type of function. All right, a function that is linear. A linear function will always be a non-vertical straight line, meaning it can't go straight up and down. But if it's tilted just a little bit, it's linear. So I'm going to highlight non-vertical straight line. What makes a straight line, especially when we're talking about on a graph, is what we call a constant rate of change. Something that's changing by the same amount over time. You can think about if you have a cup of coffee sitting on a table. It's going to cool down the same amount over a period of time. It'll drop a few degrees 1 hour. The next hour it'll drop another few degrees. It'll keep going. It's not going to drop 10 degrees, then stop, wait half an hour, then drop another 10 degrees. It's going to go down by the same amount over a period of time. We call that a constant rate of change. Vice versa, a nonlinear function does not have a constant rate of change, meaning anything that moves in kind of and not a pattern. So you could say like your height as you grow older, that would be an example of something that's non-linear, because you're not going to grow the same amount each year. You may hit a growth spurt. You may not grow for a year. You may grow all at once. All right, something that's non-linear does not have a constant rate of change, which means it would not be a straight line. And that's what we're going to start with, just identifying whether some things are linear or non-linear based on a graph. We have this kind of U shape here, which we'll talk about what this is and what it means when we get to second semester. But think that if you were on a sled or a skateboard and you're going down this graph, you're going to go really fast because you're going almost straight down. As you kind of reach the bottom, you'll expect to slow down. As you go back up, momentum, you won't go as fast. There's not a constant rate of change through here. It's also not a straight line. So now this is not a linear graph. For explanation, we could say it's not linear. And our explanation would just be, it's not a straight line. This is what we would call a quadratic. That's a different type of function. We're talking about functions in general. There's kind of three types of functions we'll talk about this year: linear, exponential, and quadratic. So this is kind of our first of our family of three. Second one, b is a straight line. It's tilted a little bit, but it doesn't go straight up and down. So this is linear. And then its reason, we could just say it is a straight line. We'll talk about kind of going forward in this chapter, but how we mark the rate of change on a graph. It's the word slope. You probably heard that you for sure heard that last year. But we could count. So we are always going like kind of 2 box over, 2 box up, 1 box over, 2 boxes up, 1 box over. Our rate of change is the same each time. All right. Next set of examples. How can we find if something is linear based on a table? Right. We have our x values, which again are inputs, our y values, which are outputs. We're going to check for a pattern between our inputs and also our outputs to see if we have a constant rate of change, if each value is changing the same amount as we go down our table. We do that with just kind of counting. To go from 3 to 6, I have to add 3. So I draw a little arrow and I say plus 3, I'm going up. From going from 6 to 9, again, I'm jumping up 3. To go from 9 to 12, I'm again jumping up 3. So for my x values, as is, the rate of change is the same. They're always increasing by plus 3. We have to check the y's as well and make sure they're increasing or decreasing by the same amount. To go from 36 to 30, I'm going down 6. So I'm going to write minus 6 here. To go from 30 to 24, I'm going down 6. To go from 24 to 18, I'm going down 6. So my rate of change is the same for my inputs and the same for all my outputs. So this would give us overall a linear function. So we're going to write off to the side. We're going to say this is linear. And for our explanation, we're going to say the rate of change is constant. So this is a phrase you'll have to remember when you're looking at a table. This is what you want your explanation to be. The rate of change is constant. The work that you're showing are these little arrows showing, all right, it's going plus 3, minus 6. You need both of these things. Check our second one by doing the same thing. Our x values are increasing by 2 each time. Still have that pattern of plus 2. We're going to check our y values now. To go from 2 to 9, we're increasing by 7. To go from 9 to 20, we're increasing by 11. To go from 20 to 35, we're increasing by 15. It's not linear because this one does not follow a pattern. It does not increase by the same number each time. So we would say this is not linear. And then we just say the opposite of this. We say the rate of change is not constant. And again, we showed our work by our arrows. The rate of change is not constant. So is not. And then the last kind of piece of our three things we're going to talk about is, what if we're given an equation? How can we determine whether a following equation is linear or nonlinear? We're going to look to see that it matches up with the form y equals mx plus b, so that first equation I highlighted off to the side. I'm just going to put this right off here. Things about y equals mx plus b that we have to be aware of. There's only one y and there's only one x. M and b are in like placeholders for different numbers. We're going to see if we can manipulate these equations so they look like this. Y equals mx plus b, where we have a number in place for m, a number in place for b. So starting off easy, example A, we have y is equal to 3x plus 9. Well, this fits as is the form of a linear equation. Where 3 would be our m, 9 would be our b, we have our y and our x. For an explanation, we would say it's linear. We just want to state that outright. For our explanation, we're just going to say it fits the form of the equation. It looks like what a linear equation is supposed to look like. So say fits the form y equals mx plus b. Going across to see example B. So this is y is equal to 3x squared plus 2. Does this fit the form? Would this be linear? Why, Luke? You're shaking your head pretty adamantly. The squared. If there's a squared in there, not linear. Wrong. It's going to have to be, just like I said, just an x. You're never going to see an exponent on there if it's going to be linear. So we're going to write down not linear. And our explanation is going to be, again, it does not fit y equals mx plus b. And even if you want to be super on top of it, you could even point out, let me just get this to reconnect. My computer is about to die, which literally means I have seconds to plug it back in. And I'm not being dramatic, it's true. Like, that's what our issue is here. That's making it not linear. So let's say not linear. I catch up. linear does not fit y equals mx plus b. All right. What about C? Are we thinking linear or nonlinear? Remember, we can move things around. Like addition works in both directions. 4 plus 2 is the same thing as 2 plus 4.
Yeah.
It still fits the form even though it's not written exactly y equals mx plus b. We could rewrite it so it looks like that. Y is equal to 3 over 5x plus 7. Now that fits exactly. So we can rewrite an equation for it to fit y equals mx plus b, then we're good to go. So we say this is linear. It fits the form y equals mx plus b. And then last one real quick. Same reason our last one was nonlinear. We have an x squared here. We also have an extra x. This would be like that first example we talked about, what a quadratic, that U shape. This is the form of a quadratic equation, all right? A big topic in second semester. I'm just gonna draw an arrow down here because we could use the same explanation.